Mr. Gasser here, Applied Physics 39. This is on springs. So here we go. So springs here, I have a bunch of springs. I'll show you right here. So spring, I apply force to pull it apart and it'll snap back. Different springs, this is a little easier to pull. Different springs will have different sort of amount of force you need to elongate it. So that's it at rest, elongated, and we usually deal with sort of hanging weights on it. So every spring has its own spring constant, which kind of tells you how hard it is to pull. The higher the spring constant, the harder it is to pull. So the formula that we're going to use here is pretty straightforward. It's on the reference table. It's right here. At force on a spring equals kx, and I abbreviated it to be this. Force on the spring, it equals to the spring constant for that particular spring, and the elongation we're going to do in meters most of the time, but it's really going to be a distance or a length. It can be in inches, maybe feet, but it really depends. But that's the formula, so we just have to apply that. In these cases, here we go, homework 39. So a 20-pound weight is attached to a spring causing it to stretch as shown in the diagram below. I'm going to use this formula here. Let's write this down all the time. F of S equals Kx. So here, the force on the spring, I made this simple. I'm just doing it in pounds. Typical physics teacher's not going to like that, but that's what I'm doing. It works for us. 20 pounds, and we're trying to find the we're trying to find K. We're trying to find the spring constant, calculate the spring constant. X is the elongation, so it's this big. It's half of a meter with no weight on it. Add the weight, it's now 1.00 meters. So the elongation here is this distance, which is going to happen to be 0.5 meters, okay? So, and then this is K. So what you want to do is you want to get K by itself. You divide this by 0.5 meters. They cancel out. 0.5 meters. And the units here is going to be pounds per meter. So that's pounds over meter. And then 20 divided by 0.5. Some people get this wrong. 20 divided by 0.5 should be 40. So 40 pounds per meter, equals K. That should just be K. That's the answer right there, is 40 pounds per meter. So that means if you put 40 pounds on the spring, it'll stretch 1 meter. For every meter it stretches, 40 pounds of force. That's what that means. Number 2, unstretched, similar thing. And this, I'm giving you the elongation, 0.4 meters. Find the spring constant. This is the formula, again, on the reference table. It explains what these things are as well. So I'll do it like this. F of S equals Kx. We know the force on the spring is 2 pounds. K we don't know. The elongation is 0.4 meters. This is a very similar type of problem. Let's get K by itself. Go like this. That cancels out. Divided by 0.4 meters. The units here is going to be pounds over meter again. Pounds over meter. 2 divided by 0.4. 2 divided by 0.4 is 5. So 5 pounds per meter is going to be K. Now this spring is much easier to pull on than this, which requires 40 pounds. So this is a much stiffer spring. This is an easier spring to pull. Okay. And different springs are used for different purposes. The spring in your pen does not need a lot of force. The spring on a big truck or on your garage door, if you have one of those, it requires a lot more force. Here we go. Now we're going to... I messed this up. Sorry, this is my fault. This should be in pounds. I'm sorry. That should be in pounds. My fault. I should have fixed that. I just missed it. So the spring constant. Now I'm giving you the spring constant and the mass of block in pounds. Mass of block in pounds. So here so it gives you the spring constant. So the force, we're trying to find the force. So now it's F of S equals Kx. F of S, force on the spring, is the weight, is what we're looking for. This is 84 pounds per meter, and that's times your elongation, which is 0.15 meters. Now, when you do that, what you have is the units will cancel out. You go like this, the meters cancel out, and it's going to give me the answer in pounds, which makes sense for force. So once you do that, that's going to give me the answer in pounds, so I have my units already. And then I do 84 times 0.15. 84 times 0.15 equals 12.6 pounds. So now you can calculate how much weight is on there based on the other piece of information, which is also necessary sometimes. Now we're going to find the elongation. You have the spring constant, you have the weight. So F of S equals Kx. Always start with that. The force is now 56 pounds. The spring constant is 45 pounds per meter, and then X is the elongation. So you got to divide it. I'll do this. You got to divide it by 45 pounds over meter. That cancels out. Divide it by 45 pounds over meter. And then what I'm going to do, I'm just going to do it right here. This is, so 56 divided by 45, you can do that math on your calculator within a second. It's the units, pounds divided by pounds over meter. That's the keep change flip. So I have pounds, and then I change the sign, and it's going to be then meters over pounds, okay? And then the pounds cancel out, and my answer is going to be in meters, and I'm trying to find an elongation, how long it stretches, which makes sense. It's going to be in meters. 56 divided by 45 is 1.24. So now I'm talking the elongation, or X, is going to be 1.24 meters. Okay? And then number 5 looks like this. I have the spring constant, I have the elongation. Now I'm trying to calculate the force on the spring in pounds, or basically the weight is going to apply the force. Now I do this. F of S equals Kx. F of S equals spring constant is 72 pounds per meter times the elongation, which is that. Okay. Now let's just do the units here. Put meters over 1. And as we've done, the meters will cancel out. Meter over meter. That leaves me with pounds. And then 72 times 1.3 gives me F of S equals 72 times 1.3 equals 93.6. I don't say what to round to, but that's fine. 93.6 pounds is how much must have been placed on there for this spring with that spring constant to be stretched that much. So that's just the basics of calculating spring constant. Mr. Gazda and I approve of this homework.